Welcome to the problem-solving session of the lecture notes for Chapter 4. Let's begin with the first problem. Here we're told, or we're asked, is the acceleration of a projectile 0 when it reaches the top of its trajectory? If not, why not? Well, the answer is that the acceleration of a projectile at all times is equal to minus g on the surface of the Earth, where g is, of course, 9.8 meters per second squared. So, at all times, a projectile is subjected to a downward acceleration, or in the y direction, which is equal to minus 9.8 meters per second squared. Question 2. A sailor drops a wrench from the top of a sailboat's vertical mast while the boat is moving at constant velocity. Constant velocity being at a constant speed in a fixed direction. The question is, where will the wrench hit the deck? A, ahead of the mast, B, behind the mast, and C, directly below the mast. And I have a video which will help illustrate the concept for relative motion.
This is what we call our steamboat demonstration. First, we're going to keep this equipment stationary, and we're going to fire a steel ball directly up through the tube. First, we'll compress the spring, then set the timer, press the button. Notice that the ball went straight up, turned around, and came down and was caught in the funnel. In this part of the experiment, we're going to launch the steamboat down the track and simultaneously fire the steel ball up the tube. The steamboat has a certain horizontal velocity, and the ball will acquire the same horizontal velocity as its launch. And this means that the ball will follow a parabolic path, and at every instant it will be over the funnel, so it will be caught by the funnel in the same way. So we'll do much the same thing. Drop the ball into the funnel, compress the spring, set the timer, and this time I have to put compressed air into the lower cylinder so the steamboat can ride on a current of air.
So, whereas in the video demonstration, we saw a steel ball that was launched upward from a steamboat, which was moving at constant velocity, the same applies here where our sailboat is moving at constant velocity and a wrench is released. It will be true that if this is our boat here, our sailboat, and we've got a wrench over here, which is going to be released, that as the sailboat moves at constant velocity, the launching of this wrench will be such that it will fall directly at a point below where it was launched, because both will be moving at the same horizontal velocity. In other words, barring air resistance and any other force which may be acting in the horizontal direction to supply some sort of a horizontal acceleration, the velocity of the wrench is only affected by the acceleration of gravity, making it fall downward. Okay, here we have another little video to help us visualize the situation. The question goes as follows. a tranquilizing dart, in other words, a projectile, is fired at a monkey, which we're going to say is a target, in such a way that the dart leaves the gun at the same time as the monkey drops from rest. So here is our projectile, here's the gun, and here's our target, which is the monkey. At the time the projectile is fired, the monkey will drop from the tree, for example. If the gun is initially aimed at the monkey, how long does it take for the dart to hit the monkey? In other words, this is the point where monkey meets dart. And so the question is, how much time does that take? Well, we'll solve it in a minute. Let's first watch the video animation for this event.
This demonstration is about a park ranger who has to shoot a tranquilizer dart at a monkey. He's going to use a blowgun to do this. In our demonstration, this brass tube is the blowgun. We're going to fire a ball bearing rather than a dart, and we're going to use compressed air from this hose to do it. On top of the brass tube, there's a laser, and if you look at the monkey, you'll see the monkey has a target attached to its stomach, and there's a red dot in the middle of the target, which is the laser beam, showing that the blowgun is pointed directly towards the monkey. We make sure that the monkey starts to fall when the ball bearing is released by putting a switch at the end of the barrel. When the ball passes the switch, it opens a circuit that releases the electromagnet, and the monkey starts to fall. Now, the ranger has not done this before, and he thinks that if he points his gun directly towards the monkey, he's going to hit it. But he forgets that the dart is going to fall a distance 1/2 gt squared in its flight. But the monkey is also naive, and he thinks that if he just lets go of the branch when he sees the dart coming towards him, he will fall out of its way, forgetting that he too will fall a distance 1/2 gt squared, and therefore fall directly into the path of the dart.
Sure enough, we see that the projectile has struck the target each and every time. Now let's go ahead and proceed to solve for the time. Now we know that the two of them will meet, that is the projectile and the monkey, when their vertical position is equal to one another. Now we've had a little disintegration here of our mathematical symbols, but let's see what we can do here. For the projectile, we've got the vertical position of the projectile minus its initial position. So this is final at the point of striking, minus initial, which is 0, so we'll leave it off for now, is equal to the initial velocity of the projectile in the y direction times t. Remember, it was launched at an angle theta, and so we will have an initial velocity for the projectile in y, which is equal to the initial velocity times the sine of the angle theta. So this is what we have for initial velocity in y. Times t minus 1/2 gt squared. Okay, for the monkey, our target, we've got its position yt, which is located here, t for target, minus its initial position. Now its initial position would be xt tangent of theta I, and you can see that because xt is the horizontal range that the projectile makes, or in other words, the horizontal distance from the monkey to the projectile. and that is adjacent to the angle. The vertical position is opposite the angle, and so the vertical position y is equal to tangent of the angle times the adjacent. In other words, the tangent of theta is equal to y vertical over x tangential. And so we can express the initial position and the final position, yt, which of course is the same as yp, minus the initial, which we're going to say xt, times the tangent of theta initial, equals minus 1/2 gt squared, because the monkey drops from rest. In other words, he doesn't throw himself downward, he's released from rest. Okay, well, we have to set these two equal to one another if they are to meet at the same place. And we're trying to figure out at what time that is going to be. So we say for the projectile, the initial yt minus 1/2 gt squared equals xt, because we're going to transfer this term to the right hand side, tangent of theta initial minus 1/2 gt squared. And you can see what is going to happen. This term will be canceled by that term, and so t, the time when they will both meet, or how long it actually takes, depends on how far away horizontally the projectile is from the monkey, times the tangent of the angle of launch divided by the initial velocity of the projectile. And if we had numbers, we would just plug these in and obtain a value for t. Let's see, how about inserting some numbers? Let's let theta initial equals 45 degrees. Let's let x sub t, the horizontal position, equal 5 meters. Let's let v initial of y equal v initial, we'll say it's 10 meters per second, times the sine of 45, which of course is the same as the cosine of 45. And that gives us an initial vertical velocity, or component that is, of 7.07 meters per second. Putting all this together, we see that in fact the monkey will only have 0.707 seconds from the time he drops before he will become the target of the projectile. Or we might say the projectile will strike the target 0.707 seconds after being launched. All right, next problem. Here we are told that to start an avalanche, an artillery shell is fired with an initial velocity of 300 meters per second and a launch angle of 55 degrees above the horizontal. We are told it explodes on a mountainside 42 seconds in flight, and we're asked to determine the displacements of the shell, both in x and y, how long it takes for the shell to reach maximum height, and the final velocity of the shell as it explodes. All right, so let's write down some of the information that's given to us. The initial velocity, 300 meters per second. The angle of launch, 55 degrees. The time for the explosion to occur, 42 seconds. And the first thing we're asked is to determine the x and y displacements. Well, to get the x displacement, we need v initial x times t. Now, is v initial x the same as v initial? Absolutely not, because since the projectile is launched at an angle, v initial x is equal to v initial times the cosine of the angle. That is because there is both an x and a y component, and so v initial x cannot be 300 meters per second, but rather 300 meters per second times cosine of 55. Well, that works out to be 172.1 meters per second. I know I'm not keeping to 3 significant digits, but that is because this is not our final solution yet. Oops, 42 seconds is the time that it's in the air, and that gives us an x component of 7,200, and this time we'll go ahead and round it to 3 significant figures, 30 meters. Okay, let's solve for delta y. Delta y is equal to, this time, v initial y sub t minus a half gt squared. Notice that we have the extra term because the acceleration is along the y direction. Here, v initial y will be equal, again, v initial times the sine of 55 degrees. You see, it's not the same as 300. So we must be very careful when solving these problems that we consider the components of velocity when our projectile is launched at an angle to the horizontal. Here we put it all together and we get, by the way, the initial y, if you're checking your numbers, should be 245.7 meters per second. Again, I have not rounded it because we have not given the final result yet. Let's go ahead and write 4.9 t squared. We substitute 42 seconds for t, and we obtain the result of 1,678 meters. So by the time this projectile strikes the side of the mountain, it has trekked a horizontal distance of 7,230 meters and a vertical distance of 1,678 meters above the launch position, okay? Because this is positive, and so it indicates that the displacement is in the positive direction. To reach maximum height, we set v final in the y direction, the y component of velocity equal to 0, because this is the point where the avalanche momentarily is suspended in the air. It's the difference between moving up versus the next instant moving down. We set that equal to v initial y t minus gt, and solving for time, we get 25.1 seconds. So what that tells us is that by the time the avalanche, the projectile has struck the mountainside, this being the launching of the projectile, this being maximum height, you see 25.1 seconds has gone by, and an additional amount of time goes by until 42 seconds minus 25.1 seconds for the striking of the mountainside. Lastly, we're asked to determine the final velocity when it explodes. This time, we are solving for Vfy at the point of explosion, in other words, 42 seconds after it's first launched. And so this time, plugging in our numbers, gives us a final velocity of minus 166 meters per second, confirming the fact that our projectile was making its journey downward when it struck the mountainside, as we would expect, since it had surpassed maximum height and was now moving or displacing itself back downward. Well, this concludes the first part of the solutions to Chapter 4 lecture problems. We will see you shortly.